Okay, guys, welcome. Today we're going to talk about planar maps and Euler's formula. Now, a planar map is a graph that is drawn in the plane so that its edges are non-intersecting continuous curves. And of course, we also assume that the graph is connected. Now, an example of something like this would be something like this, maybe. Right? So it's drawn in the plane, its edges are non-intersecting continuous curves, and we also assume that the graph, of course, is connected, so something like that. So this divides the plane into separate parts, which we will call countries. Now, exactly one country is infinite and the rest are finite, right? So in the example that I've drawn, the one that's sort of outside here is the infinite one, and those other four would be the finite ones. Now, Euler's formula gives us a way to find the number of countries in a connected planar map if we know the number of nodes and edges of that graph. Okay, so Euler's formula says that the number of countries plus the number of nodes is the number of edges plus 2. Right? We're going to sort of see how this comes about. Okay, now to prove this, we're going to imagine that we have this planar graph considered right here. Right? And the idea is that we're going to consider this to be a graph of dams and watchtowers, where the dams are the edges and the watchtowers are the nodes. Right? So in this case, we have 14 nodes or 14 watchtowers and 7 basins, and there's a little typo there, including the C, right? Because you have 1, 2, 3, 4, 5, let's see, 6, and then the outside one would be 7, right? So something like that. Now, let's imagine that we have this graph, okay? Now we're going to imagine that enemies attack the island and they want to flood the entire island by destroying the smallest number of dams, right? So one possible thing that they could do is to do this. First, break down this dam that would flood this area. Then break down 2, which would flood this one. 3 would flood this one. 4 would flood this one. 5 would flood this one. And then breaking that dam would give us the 6 that we need. Okay, so it looks like we needed to destroy 6, right? Now, in the general case, let's denote the nodes by V and the dams by E and the number of bases by F, including the ocean. So we want to flood the F-1 basins, right? And we saw that to do this, we needed to destroy exactly F-1 dams, right? Or in this case, F-1 edges. Okay, so now what is surviving? Okay, well, if we look at the surviving dams, it looks like there are 13, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and 13. So 13 remain, and we also get that the remaining structure forms a tree. Okay, so now that we have a tree that's left over, we're going to use the fact that if a tree has V nodes, then it has V-1 edges, right? So in this case, 13 dams remain, and it looks like we have, let's see how many nodes, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, right? So of course, we could have just used the formula that if we have V nodes, it has V-1 edges, right? And of course, in the general case, we have that F-1 dams survived, which are E, were destroyed, and V-1 survived, right? So we know that if we add these two together, we'll get what we started with, right? The number of edges that we started with. So the number of dams that were destroyed is F-1, V-1 survived, and if we add those two together, we get a total of E. So of course, after we rearrange, we get F plus V is equal to E plus 2, which is exactly Euler's formula. Okay. Now, as an example, suppose that a connected planar graph G has 15 vertices and 17 edges. How many faces does G have? Oops. Well, of course, we're just going to use the formula V plus F is equal to E plus 2. And here we know that the vertices is 15, and the edges is 17. So we plug them in, and we'll find that f is equal to 4. Right? So we get that this graph would have 4 faces. Okay. Now, it turns out that when Euler found his formula, he was studying polyhedra, which are, of course, solids bounded by plane polygons. So, for example, you have things like the cube, which is familiar to you, and that has 8 vertices, 12 edges, and 6 faces, right? So if you were to draw a cube, right, the way that we usually draw it is something like this. So that would be 4 vertices and 4 edges right there. And we also do one back here. So that's another 4 vertices and 4 edges. So I shouldn't draw any more vertices because that's all of them. And now I have 8, 9, 10, 11, 12 edges. And if you count the faces, it looks like you have the bottom, the top, and then the left, the right, and then the front and the back. Right? So we do get 6 faces there. Right? And you can extend this to, for example, the tetrahedron, triangular prism, pentagonal pyramid, dodecahedron, and icosahedron. Now, the dodecahedron has regular pentagon faces, and it's shown right here. And the icosahedron has regular triangle faces. It looks something like this. Right? Now, if you stare at this table long enough and you look at Euler's formula, right? Right, v plus f equals e minus 2, it looks like that's going to hold in all of these cases, right? So for example, if you do for the cube, 8 plus 6 is equal to 12 minus 2, we're going to get, oh, wait a second, I think I have this, oh no, I messed this up, right? Plus 2, yeah. So we get 14 is equal to 14. And of course, that happens every single time, right? So we, of course, have that the number of faces plus the number of vertices is the number of edges plus 2. Now, one thing to keep in mind is that this will only hold for solids that if they were blown up like a balloon would become spheres, right? So in other words, there's no hole in the middle. So if you were to have something like this, let's just say maybe we have, let me erase that. So maybe something like this. And then maybe that back edge is connected to maybe something like that. And where this is hollow in the middle, this would not work anymore, right? So just keep that in mind for this. So the reason why this works for these is because if you were to sort of push the inside out towards the edges, you would get a sphere, right? And that would only work for shapes of that form. Okay, so that concludes this video on Euler's formula. I hope you enjoyed, and I will see you next time.